Hello. So today my plan is to go through this um, three parts demo. And basically, what we are going to show is that we are going to discuss speculative decoding as one technique for speeding up large language models decoding phase. So in so I'm going to review speculative decoding. I'm going to show some code for speculative decoding for the first part of this video, and I'm going to show some code on how I implemented the speculative decoding and run that code. That's the first part. And then I'll we are going to have two other videos, part 2 and part 3. In part 2 and part 3 we are going to use AI tools in order to implement speculative decoding. So our overall goal is to basically discuss almost recently algorithm that has been developed by researcher almost 2 years ago in the area of generative AI. Then also use AI coding tool, specifically Cursor, to see if AI is able to implement that algorithm, speculative decoding algorithm, successfully or not, and then iterate on that in case by testing the AI code and then iterating in order to make the code, see how far or how close AI is to implementing kind of new ideas, okay, and helps us to speed up the implementation. Okay, let's get to the first part. So as I mentioned, the first part in this video that we are going to talk, we are going to quickly review LLMs, okay, and then after that we are going to talk about this speculative decoding paper, and then I'm going to showcase a notebook that has the speculative decoding code. So let's start with the GPT architecture. So let's go back, find it better. Okay, cool. So essentially what we are going to talk very quickly, give me a sec. Okay, so in the transformer architecture we have two parts. We have encoder, where we feed our inputs and then we calculate the embeddings, and then we have this self-attention layer, and then we have feed forward layer, and then at the end of the encoder we basically have one embedding per input token. And here the tokens, you can think of tokens as subword, let's say in average 3 to 4 characters. So we have a, let's say, sentence, or we have a piece of code, we feed it to our tokenizers, we have tokens, we chunk that a string of text or a string of code into small pieces, we call them token, and then we basically run this neural net, and then at the end of it, for each token we have an embedding. And think of embedding as a vector, let's say 768 dimensional vector that represents each token or each piece or chunk of input in n-dimensional space. So we are not going to talk about this encoder part. A good example of an encoder is BERT. Today we are going to talk about large language models that they are having this decoder architecture. And the decoder architecture or LLM architecture, the nice thing about them, if you think at the high level as a system, our input are going to be a prompt, okay? Let's say we ask a question, what is the capital of France? And then we feed that to this decoder architecture, a bunch of layers, and at the end what we are going to get, the answer to our questions, okay, in multiple kind of steps. And how that works is basically we feed our prompt to the decoder, we get the embeddings of our tokens for our input prompt. Here we feed the input to a mask multi-head attention. So this is mask basically attention, which is different than encoder attention. And then we have this multi-head attention that takes the basically in this case we don't have this connection, but we basically uh, feed the output of this mask multi-head attention, and then we have a bunch of other layers including the add and normalization layer and feed forward layer, and then we have a linear layer, and we have a softmax at the end, which means that we will have the likelihood of all of the vocabulary tokens. Okay, let's say if we have 50,000 vocabulary tokens in our vocabulary, for each token we have a likelihood, a probability that they sum to 1. And then we will have a sampling technique. Based on sampling techniques, we predict the next token. Now the challenge is that when we basically feed our prompt in, let's say, questions to our LLM, and we want to get the answer, we have to repeat this, okay, for each token until we reach to end of sentence. So essentially, when I say what is capital of France, the answer might be the capital of France is Paris. So the capital of France is Paris. So there are almost 5 tokens. So we have to repeat this, and we get basically the output 1 token at a time. And that makes the LLM, and we call this step decoding, and that makes the LLM, because it has autoregressive architecture, it makes it slow, because it's kind of time constraint. We have to generate this 1 token at a time, especially if our model, if our large language model, let's say we are using GPT-4, is a big model. This is a huge kind of model with lots of parameters. It's going to take a lot of memory, and it's going to be much more slower in terms of throughput and token generation. So me as a user, I have to wait quite time, let's say in order of seconds, in order to see the answer to my question, which is not ideal. Now, the researchers in the last 2 years, they have come up with a bunch of ideas to speed up this decoding. One of these smart ideas was proposed almost 2 years ago by some researchers at Google, and they call this technique speculative decoding. So it's a sampling technique. It's not that complicated. It's kind of to some extent intuitive. And what you do is this. So let's say we have a prompt and we feed it to a big large LLM, and we want to generate the response. Instead of giving the prompt to a big large LLM with a lot of parameters, we use a twin, or not twin, we use a sibling of that target LLM, a smaller size LLM. I will show you in the code. And then essentially with using a smaller size LLM, we can speed up the generation of those answers. And then we prompt our smaller model, and we sample, let's say, 5 tokens at a time from the small size LLM. But what we do is that when we sample 5 tokens from the small LLM, we take those 5 tokens and we pass them to the main LLM that we want to use for, let's say, code generation or for answer generation. But this time, instead of kind of doing autoregressive, we have the base prompt, and then we put these 5 tokens that we got from basically the first model, we call that draft model, and then we feed it to the second main model, we call that target model, and then we basically we feed that through all the layers. And then what we do is that as one batch we feed everything, and then we get the likelihood of all of the tokens in our response. Now when we have the likelihood from basically the first 5 tokens, let's say k tokens, or here lambda guesses that we got from the draft model. We have those likelihood from the first model. We also have the likelihood, all of the likelihoods from the target model. We call them PIs, P1 to P lambda plus 1. We have all of those likelihood. We also have the QIs for the same tokens that we generated from the draft model. Now there is a smart way of comparing them. So by comparing P and Q, we can guarantee to sample okay, our tokens from our real target distribution, which is P. And essentially what we do is that we compare the likelihood of draft model with the likelihood of the target model. If the likelihood of target model is larger than draft model, it means that we are confident that token is a good token. Okay, so we accept that token. Okay, however, if the probability of a token is less than the probability of that token from the draft model, that means that there is not certainty. So we flip a coin with probability of P divided by Q as shown here. And if the so we use this P divided by Q as the head probability, and if our coin comes head with this probability, we accept that particular token. But if our coin comes tail, we will reject. And as soon as we reject a token, okay, we are not done yet. We come to this last part, meaning that let's say if we have only accepted 3 tokens while we had, let's say, lambda guesses from the draft model, let's say 5, but we only have accepted 3 tokens, we have one more bonus token. And what does that mean? We will sample the very last token after the rejection when we exit the loop, because of this P divided by Q came as tail. We will sample the last token from this distribution. We will take the norm and then max out the delta between the target model and the draft model. Okay, and we sample a token that way. So in the appendix of this paper, if you go to the appendix, I think they have mentioned the appendix. I think in the appendix of this paper, they have give me a sec here. In appendix A1, they have proven that if we follow this algorithm, this speculative decoding algorithm, the tokens that we sample will have the same distribution as if we were sampling them directly from the target distribution. However, by using this technique, because we do the autoregressive part on the basically the draft model, which is let's say 3-4 times smaller, we can speed up the token generation by a factor of 2 to 3x. Okay, so this is the paper. Now let's go to the implementation. So I have this repository, speculative decoding. So I implemented this almost 5-6 months ago, last year, and I have some description here that you can follow in the README, but I have a notebook that I'll quickly walk you guys through it to understand how the logic works, and then we can run it. So let's run this in Google Colab. Essentially, the first step, we have bunch of imports. We import the transformers, we import torch. Okay, so that's the first step. And then essentially the first step is that we use OPT 125 million parameters, which is a Facebook small large language model as a draft LLM. So we load the draft model, we load the tokenizer, we make sure that they are on CUDA device. So let this part run. I mean, here I don't think that they have CUDA. I don't think that we have access to TPU because of the probably competition on Google Colab. At the moment, we couldn't get CUDA, but or yes, maybe we did get CUDA. So here I have a simple draft model that I implemented, but essentially what I'm doing is that I'm passing a parameter k to be 5. So here we are not doing anything crazy. We essentially feed the prompt, and then we basically generate the logics, and then we get the logics for the next token, and then we run the softmax on it, and we sample from the probabilities. Basically, we take the what do you call, we take we sample the token with the maximum likelihood as the next token. So here we basically for example, here say Paris is the capital of, this is my prompt, I pass it to the draft model. okay, and my draft model came with this basically 5 next token, the French Republic, okay, which is kind of wrong. That shows how the draft model might make mistake. Keep in mind that the intuition behind this speculative decoding is that lots of time the tokens that we are predicting are very easy tokens to predict, so even a smaller size LLM could predict them successfully. So you don't need a crazy size model, because those tokens are mostly, you know, kind of common knowledge as opposed to special knowledge. Now the second part, I'm loading the target model. So let's pretend this is kind of simulation. This is our bigger size model, let's say 3 times bigger. This is same family LLM, but 350 million model. So I load that model. Let's look at this vocabulary size for the draft model and the target model. They should obviously share the same vocabulary. That's important because we are kind of pairing these two models. Now I have implemented a similar method to the other method that I showed you, but for the target model, which means now if we feed the prompt to this method, what it does, it uses the target model, and using target model it generates the logits, okay, and then we turn the logits here. I just squeeze them, I get rid of the batch, and essentially I get all the token IDs, and then I mean this part is basically the input token IDs, but here I'm getting turning the logits to by passing this to softmax, I get the likelihood. And what I'm going to do is that I'm going to, for each token in my prompt, I'm going to get the likelihood, okay, from the target model. So let's run this. Here I have a method that I literally implemented this piece. So is a basically I use AI, I use ChatGPT, and I implemented basically if I have two distribution P and Q, it just simply implement this. I have two, let's say, array for P and Q, the two distribution. I pass those P and Q and simply uses NumPy to does that math. I mean, here I have a test case that you guys can evaluate. Here this is also very kind of boilerplate code. It's not that kind of important code. Essentially this code, what it does, it just take token IDs and convert them, decode them, and convert them to the literal kind of English tokens, so we can review them manually to see. But the main piece is main logic is here. So let's call this speculative sampling algo. This is essentially implements this algorithm one from their paper. So this is the implementation. So here what we do is essentially we implemented that these exact steps, and you can follow it later. So we have a base prompt. We also have the token IDs that we got from the draft models, as well as we have all of the probabilities from the draft model. So what we do, we first get the probabilities from the target model, and then we go through the loop, and then basically do the steps that we just went through in the paper. By computing the P, the probability of a token from the target model, basically the probability of a speculated token from the target model, and also having the Q, probability of the token from the draft model, and we compare them. If P is greater than Q, we accept it. Otherwise, we flip a coin with probability of P divided by Q. And then if that basically coin comes head with this likelihood, then we accept that token and we keep going through the loop. Otherwise, we are rejecting, okay? We are rejecting because the coin didn't come as a head. So what we do now, we have one more chance. If I'm not mistaken, if I haven't made, I might have made a mistake here actually. Wait. I have to review this, but I might have made a mistake here. I need to spend more time, but essentially this is where I'm basically sampling the very last token from this distribution, and this is something that worth kind of reviewing later. And then this is our bonus token essentially, and then after that I break from the loop, and then as we kind of go through the loop, we add the tokens to the accepted tokens. So in the worst case, we always have one token accepted, which is means that we always are as slow as just passing everything to the target model. Okay, now here basically I'm running the speculative sampling, and as you can see, Paris is the capital of the French Republic. Okay, we pass this to our method and it evaluates the, which is the first token, and then what it does uh, is kind of rejected because for the first proposal the p is less than q, p divided by q is 0.744, and then when flip the coin it didn't come heads, so it rejects, and then it sampled the next token, which is France. Okay, so the answer, okay, from our speculative decoding is France, which is correct. But if you rerun this, you might get different response. See, this time I got basically the tokens that I accepted was the French Republic, okay, which is not the correct answer, but that's the nature of LLMs, because they are probabilistic models, they are not deterministic, so we are dealing with randomness. Okay, so we are dealing with different type of machine if we consider the LLM as a computer. Okay, let's save this. So this is essentially my video. I'm going to stop here. Sorry, there is one more bug here that I have to fix. Let's do this. Okay, clear all outputs. This should do it. I think there is a issue with Google Colab. If you don't do that, okay, I cannot preview it in the. So essentially, this is the notebook that we just went through. Again, this is if you go to my repository, this is public speculative decoding K Jahan speculative decoding. You can see this notebook that we just went through, which is speculative sampling OPT. Okay, I'm going to stop and then see you in the next video where we are going to start using cursor. Thank you.